Uh, Look, I'm really happy to be able to join this conference at a very short notice, and I'm thankful. Whenever there is invitation for examining a thesis or visiting institutions in India or to give a talk, I never say no. The reason is rather simple: that this country invested a lot in my education, in my growth. I did work for Department of Atomic Energy in Kalpakkam for about 8 years, and I consider that place as my alma mater. That's where my research training happened. So I seldom say no. This is one little way of giving back to the country which invested in me. Today I'm going to talk to you about graphene. About graphene, there are few words in the title which I have highlighted intentionally because those are the catchwords. So what I'm going to show you today, I believe that it is innovative, it is disruptive, and we will be talking about graphene in the context of corrosion resistance. My name is Raman Singh. I come from Monash University in Australia, and I published under this name. This was my original name when I was in India, and I still publish under this name. But my official name at Monash University is what you see, Raman Singh. Okay, why corrosion? Just again confirming that I'm audible and my slides are visible. Is that correct?
Yes, sir.
Thank you. So, um, corrosion costs heavily. In fact, it costs an economy like USA about $300 billion. If you take every cost related to corrosion into account, like why you need to use stainless steel, or why you need to have coatings, why you need to use copper pipes, and so on and so forth, it turns out to be that kind of figure, $300 billion every year. Any developed or developing economy loses about 4% of its GDP through corrosion. And it is an expensive affair, and you can see variety of different sectors contribute to this huge loss. Because corrosion has been an old problem, and and expensive problem, people have been doing variety of things for addressing it, like just now I mentioned about corrosion resistant alloys, stainless steels, or aluminum alloys, or they have coatings like polymeric coatings that you have on your cars, or variety of coatings. These measures have handsomely contributed to the mitigation of corrosion. There's no doubt about that. But there is no permanent solution. There is no such thing called everlasting coating. Every coating eventually fails because of chemical attack, because of mechanical damage, so on and so forth. So the point that I'm trying to bring home is that because corrosion has been an old phenomena and expensive phenomena, people have done almost every type of thing that they could explore for mitigation of corrosion. And again, I'm emphasizing that point because I want to let you know that doing something novel, doing something disruptive is scientifically very challenging because people have explored most of the things. But if you could do something disruptive, it is commercially hugely rewarding because corrosion is an expensive phenomenon. So what I'm going to show you today through this talk is that if you take a bare piece of nickel, and these are the kind of things you will be seeing through the talk, and you expose it to the corrosive solution of sodium chloride, it will be damaged very soon. But if you had graphene coating on that, it will last perhaps forever. There may not be any corrosion at all. And that's the kind of thing that I'm going to show you.
Sorry to
Also,
interrupt you, sir.
yes,
Sir, your slides are not moving. It got stuck on the first slide. So if you
okay,
want to make them move, then you have to, yeah, you have to
yep,
just click on them.
okay, that's fine. Is it moving now?
Yes, sir, sure. Thank you.
So I talked about bare nickel. It will be finished very soon. If you have, if you don't have coating, with coating it will last for long time. Also, what I will show you, and this is what is disruptive and novel. that developing graphene on mild steel is is um, is technically or technologically prohibitive. It is very difficult or impossible to develop graphene on mild steel for the reason that we will discuss later. So we were the first people, and this work has been published just a few months ago in a very reputable journal, as you can see, uh, that we have been able to develop graphene on mild steel, and that graphene has given very good corrosion resistance, about more than 2 orders of magnitude superior corrosion resistance to mild steel. Without coating, mild steel will be corroding very fast, and you can see it improved. This axis, which is impedance, gives me measure of the corrosion resistance, and that corrosion resistance sustains for long time. And for the regions that I will be discussing in a while, that there is no reason why it should not be everlasting. This coating will not degrade over a period of time. This was patented earlier, and also this work was awarded in a competition in Boston a few years ago. Also, when you have graphene coating on nickel, irrespective of the aggressiveness of the environment, the corrosion resistance is same. That's what this slide shows. The intercept of these two arms gives me corrosion resistance, this point. And this point is same in every plot that I'm showing you. And that shows that corrosion resistance of graphene coated nickel is same irrespective of whether I'm testing in highly aggressive sulfuric acid, or I'm testing in aggressive sodium hydroxide alkaline solution or neutral solution. Whereas the uncoated one has different behavior. That uncoated one corrodes very, very rapidly in acidic solution. In alkaline solution, it passivates very fast. So that's the behavior, and it is different in sodium chloride solution. So the uncoated nickel behaves differently in different solutions, but the graphene coated one gives same corrosion resistance. And post-corrosion morphological characterization have given explanations for those. Also, we developed graphene on nickel copper pure alloy, and we got extraordinary corrosion resistance in sulfuric acid. It's highly aggressive solution, but this test or this data is quite suitable, quite applicable for this kind of fuel cell, proton exchange membrane fuel cell. Their bipolar plates have very demanding situation, and in this environment, there is very little corrosion damage. Again, it is polarization plot where the intercept of the two arms gives me corrosion resistance. This is what is called electrochemical impedance spectroscopy plots, where again the impedance value at the lowest frequency gives me corrosion resistance. And this is unique behavior for this particular material, that over large spectrum of frequency, there is no change in impedance. This is for the first time we saw some behavior like this. And as you can see, graphene coated alloy, particular alloy, pristine alloy, nickel copper alloy, does not undergo much corrosion at all. But if you didn't use proper alloy, the graphene starts to get disrupted, and that's why behavior is not as good, this green plot. Okay. And again, this work was published as second paper in this journal. As I said, that's a highly reputable journal, and this work has been published just a couple of months ago. So what is graphene? We know about graphite. Graphite has layered structure, as you can see here. Graphite has layered structure, and if you separate one single layer, that is graphene. If you did that before 2010, you will be winning Nobel Prize. Nobel Prize was awarded just for separation of graphene from graphite and proper characterization of that graphene. So this single layer has honeycomb type of structure. Every node here is sp2 hybridized carbon atom. It is 2D, two-dimensional material. If you make a ball out of it, it is carbon buckyball, which was awarded Nobel Prize as well. And if you make a tube out of it, it is carbon nanotube. So that is graphene. Why graphene is so attractive? Why people have spent so much time and money and research resources on graphene? Because graphene has extraordinary properties, electrical properties, thermal conductivity, electron mobility, surface area, a few orders of magnitude superior compared to its competing materials like metallic materials. Last three properties are most important properties of graphene for its application as corrosion resistant coating. Graphene is very strong material. For the same thickness, graphene is 100 times stronger compared to the strongest steel. And at the same time, it is tough. Those who are from mechanical property domain, they will know that strength and toughness are opposing properties. The material that is very tough will generally have very poor toughness. It will be brittle, like ceramics, has very high strength, but they are brittle. As opposed to that, graphene has both strength and toughness. Graphene is also chemically inert. Even highly corrosive hydrogen fluoride cannot attack or does not attack graphene. So it is important because quite a lot of coatings, like polymeric coatings, they degrade because of chemical or physical interaction with the environment. Like polymer coatings can degrade because of ultraviolet ray or because of alkaline environment. Also, graphene is highly impermeable. That little hole that you have in the middle of the hexagon is so tiny, so small, that even helium can't pass through it. So the species that cause corrosion, like water, H2O, or chloride ions, or oxygen, these are the agencies that can cause corrosion. They don't have any chance of passing through it. It is so tiny, that hole. So what I showed you, that graphene is impermeable, even smallest fluids. Graphene is both strong and tough, and graphene is inert. There is no other material which has all these three properties in one material. And that's why question is, can graphene be an ideal barrier for corrosion resistance? The first work happened on this topic just a year after the Nobel Prize that was awarded in 2010. And Rod Ruoff's group from Texas, what they did, they took pure copper and graphene coated copper, and they exposed it to air at 200 degrees Celsius, and they found that pure copper oxidized. That's why change in color. Graphene coated one did not oxidize. And they did similar experiment on copper nickel alloy, and they found that copper nickel alloy did change the color. Graphene coated one did not change color. They did another experiment where they took a penny, and upper half of the penny was coated with graphene, and they dropped the entire penny into highly oxidizing hydrogen peroxide environment, and you can see that upper half did not undergo any corrosion, no tarnishing, no corrosion. Lower half, which was not coated with graphene, did undergo tarnishing. We were perhaps the first people to do systematic characterization of corrosion of graphene coated copper and other materials. And quite a lot of people, Nikita Chitre is a PhD student currently under the IITB Monash Research Academy program. Then following four people, Abhishek Arya, Sanjid, Anisur, and Abhishek, they were my PhD students who worked on graphene. And then there were other students, Lokesh, who is in Philips in USA. Parma Banerjee was a student then. She is now senior lecturer at Monash. She is my colleague. And other PhD students, Manak Majumdar was junior academic there. Now he's full professor. And last five names are very important. They are undergraduate students who worked on this topic. So first, graphene coated material we got from our colleague Ajian. He is very well accomplished and world famed scientist in 2D materials. We got graphene coated copper and pure copper samples, foils from Ajian's group. And first job we had was to establish that what we got had graphene coating. So the lower sample is what they said graphene coated one. When you do Raman spectroscopy, you get signals or you get spectrum to confirm whether you got the graphene or not. Graphene has this typical spectrum where you have G peak. This peak is G peak and 2D peak. And the presence of these two peaks confirm the presence of graphene. And and then what we got from Ajay's group had graphene, and that is the critical information, confirmatory information about graphene. But this spectrum also gives me another very important information. The ratio of the intensity of G and 2D peaks gives me number of layers of graphene. So for single layer graphene, G peak is shorter, dwarfer compared to the 2D peak, whereas if you increase the number of layers, G peak becomes taller and taller with respect to 2D peak. So ratio of the intensity of G and 2D peaks gives me number of layers of graphene. And in our case, we had single layer graphene because G peak is shorter, dwarfer compared to 2D peak. And of course, the pure copper does not show these peaks. This other little peak is D peak, which gives me idea about the defects in graphene. So we got this graphene coated copper and pure copper samples from Ajay's group. We did typical corrosion tests, which is polarization test and electrochemical impedance spectroscopy, is similar plots that I showed you earlier. And you can see that intercept of these two once again gives me corrosion resistance. What I'm trying to show you here is that intercept here for the graphene coated sample and the pure copper sample. If you compare, the graphene coated one has 100 times smaller current. Lower the current, the better the corrosion resistance. So just one atomic layer thick graphene improved corrosion resistance of pure copper by 100 times. Just one single layer, right? And that was confirmed by electrochemical impedance spectroscopy. As I said earlier, that impedance at lowest frequency is a broad measure of corrosion resistance, and you can see 2 orders of magnitude superior corrosion resistance due to graphene coating. And that was confirmed later by post-corrosion microscopy. Around the same time, others were also working on this particular topic, and we were getting varied results. We were getting different results. Our group was reporting more than 2 orders of magnitude improvement. Another group from USA was showing less than 1 order. Another group from Monash was showing not much improvement at all. So what was going on? Why we were getting different results for the same type of material? And a good researcher, particularly students who may be there in the audience, it's very important to keep in mind that just feeling very good that, oh, we got best results is all right, but really you should look into why others were not getting. When we were showing this kind of varied results that we are getting improvement by 2 orders of magnitude and someone was not getting much improvement at all, in the middle of that, we got a paper which says graphene coating, as a matter of fact, accelerates corrosion. We were talking about improvement in corrosion resistance. This paper, published in a very reputable journal, says that it accelerates corrosion. As if one was not sufficient, another group, it says graphene, see the title of the paper, graphene as a long-term metal oxidation barrier, worse than nothing. Means if you don't have coating, it will be performing better. It will be giving you better corrosion resistance. The point that they were missing is that wherever graphene was intact, corrosion resistance was intact in those areas. Where there was disruption in the coating, corrosion was worse there. And they showed it in their schematic diagram that wherever you have breakage in the coating, corrosion was getting accelerated at that location. And which is not surprising at all. When we published our paper before them, we clearly mentioned that your coating has to be continuous. If you have disruption at the location of disruption, corrosion will be higher for the simple reason that graphite is highly cathodic. If you attach it to anything, it will undergo corrosion. And that's what was happening here, that highly cathodic graphene was forcing the bare area to suffer corrosion at higher rate. So that was the reason. And we had mentioned that in our paper that we published earlier. Graphene has another problem that it has, when it is developed by chemical vapor deposition on metal, it invariably has the problem of these boundaries. That, and the first paper by Rod Ruoff, he also showed that there is corrosion at the boundary. He didn't mention, but the micrograph clearly says. Graphene has another problem of wrinkles. Why? Because graphene is one of the rare materials which has negative coefficient of thermal expansion. What does this mean? That when you cool graphene, it expands, unlike other materials. So when you do chemical vapor deposition, the metal underneath contracts upon cooling, whereas graphene expands, and that leads to formation of more and more wrinkles. And those wrinkles are problem, because at the top of the wrinkle there can be so much stress that it will crack, and corrosion can take place exactly at the wrinkles. People showed this. So what I showed you is that graphene can have problem of this kind of inter-domain boundary. Corrosion can happen at that place. Corrosion can happen at wrinkles. There is another problem. There can be point defects. In place of hexagonal structure, you can have pentagonal or heptagonal structure, and those are point defects. And those are also not very good for corrosion resistance. So when the first student joined to work on this project, we came up with a hypothesis, that is, that if we have multi-layer graphene in place of single-layer graphene, that could be good, that will be better for corrosion resistance. And the reason behind that hypothesis is very simple, that if you have single-layer graphene, you may have disruptions, and at the disruption, at the site of disruption, there will be greater corrosion happening because of cathodic nature of graphene. But if you have multi-layer graphene, then it is likely that the disruption in the first layer will be masked by the upper layer, if not one, by the second layer. So with that hypothesis, we started to, in fact, we showed that if you have graphene, you can see that there are wrinkles in the lower layer, but where you have wrinkles in the lower layer, that is masked by the upper layer, which may itself have wrinkles. So we could show that was the purpose of the hypothesis. So we started to develop our own graphene. I will quickly go through how we develop graphene by chemical vapor deposition. You take the metal on which you want to develop graphene, that is copper or nickel. And why copper and nickel? I will talk about that in a sec. So you take copper, place the copper inside the furnace, you pass hydrogen and you heat it to 900 to 1000 degrees Celsius. And why you are passing hydrogen? Because every metal has a native oxide, a layer of copper oxide. In this case, copper oxide will react with hydrogen and water will be pumped out and pristine copper will be left behind. And you need pristine copper because copper and nickel are very good catalysts for splitting hydrocarbon. So when you supply hydrocarbon in a very controlled way using this mass flow controller, that hydrocarbon will be split into carbon and hydrogen. And if you maintain right partial pressure, you will have graphene. If you did not maintain right partial pressure, you can have carbon nanotube, you can have diamond, you can have carbon soot. So supplying hydrocarbon at a controlled rate is essential for developing graphene. Otherwise, you will get something else. And that's how you develop graphene, and that's how we develop our own graphene in our own lab. So how do we, and also I would like to mention one particular thing, that there is a stark difference in the mechanism by which graphene develops on copper and graphene develops on nickel. As I said, both copper and nickel are very good catalysts for splitting hydrocarbon that is required for graphene development. Copper does not have much solubility of carbon. So whatever carbon you generate, it immediately arranges itself to develop graphene if you maintain right partial pressure. So copper can only develop single or two-layer graphene because the carbon that you produce, it cannot dissolve in copper, which has very poor solubility, very low solubility, insignificant. Whereas nickel has very high solubility of carbon, as you can see here. So whatever carbon you generate here, it diffuses into nickel matrix, it saturates the matrix, and then when you cool down, then carbon is rejected because solubility decreases with decreasing temperature. And again, you have carbon diffusing out, and it develops graphene. And that kind of graphene can be developed as multi-layer graphene. So nickel can develop multi-layer graphene. Copper can develop only one or two layer graphene because copper does not have much solubility. Keep that in mind because we will use that later. So using that setup, we developed our own graphene. That graphene was multi-layer. As you can see, G peak is taller compared to 2D peak, but the graphene had lots of defects because the tall D peak. So we could get improvement of only 10 times or so using our own graphene, but that was not the main purpose. Main purpose was to show that this graphene gives durable corrosion resistance. This student could do tests up to 400 hours, and whatever corrosion resistance was observed after a couple of hours, that sustained for 400 hours, that entire test duration. So first time we could show that if you had proper graphene, and in this case it was multi-layer graphene, the corrosion resistance is durable. That is unlike what was reported in those two publications in very reputable journals. So first time we could show that yes, you can have durable corrosion resistance. Later on, we improved the CVD, or chemical vapor deposition parameters, and we could show that graphene on copper can give longer term corrosion resistance. But keep in mind that we had our interest in developing graphene, multi-layer graphene, which is easier. Developing multi-layer graphene is easier on nickel. So our future work primarily focused on nickel. And to cut the long story short, I don't have time to go into details. We could show that if you do rapid cooling after CVD, and in the environment devoid of hydrogen, in the environment without hydrogen, then you develop graphene with less wrinkles, and we don't want much wrinkles because wrinkles are bad for corrosion resistance. But if you did slow cooling without hydrogen, you end up not developing any graphene. Or if you did rapid cooling with hydrogen, again, not much graphene. And we proved that we could characterize that using Raman spectroscopy, as you can see here. Right. And that graphene, in fact, the graphene that is developed with rapid cooling after CVD and without hydrogen gave corrosion resistance that is stabilized after some time, and that corrosion resistance continues for more than 1,000 hours in this highly corrosive chloride solution. And there is no reason why this will not last forever. Why I'm making that statement is simply because the deterioration in corrosion resistance can only happen if coating deteriorated, and my coating will not deteriorate. It does not. It is inert. It will not be chemically attacked. It is impermeable for the reasons that I showed you earlier, and also it is tough. That it will not get mechanically damaged because it is tough. So there is no reason why it should not. But if you impacted it, if you broke it, then there is a dangerous situation. But if the coating sustained, then it will be everlasting. It will not be undergoing much of chemical damage. And this you have seen earlier, bare nickel undergoes corrosion even in 2 hours. This is after 2 hours, but graphene coated nickel, even after 1,000 hours in this corrosive solution, does not show much of corrosion. It was recently published. Then we started to look into whether we can apply it to real life situations. And earlier we had worked on copper coated with graphene, and we showed that there is some that can be useful for this kind of fuel cell bipolar plates, which I described earlier. And this is the configuration of the bipolar plate. And we showed some improvement. We also worked on graphene coated monel, which is copper nickel alloy. But if you have pure nickel coated with graphene, multi-layer graphene, it showed very good corrosion resistance, and these are all published results in very good quality journals, JPS and Carbon. Then we started to show that it is long term, it is durable corrosion resistance in this highly aggressive sulfuric acid environment, and corrosion resistance sustains for more than 700 hours. And again, post-corrosion analysis, bare nickel in this highly corrosive solution will be finished in no time, whereas graphene-coated nickel showed very good corrosion resistance and post-corrosion uh, imaging confirmed that. So what I showed you so far is that we could develop graphene on copper and copper nickel alloy, and they showed very good corrosion resistance, but we worked on very small samples. Can we develop this quality graphene on large area? And more importantly, can we develop graphene on alloys which are of common use, like mild steel? And as I said earlier, as I alluded to earlier, that it is challenging. So we started to work on improving our parameters. Earlier, we used to have flat samples in the CVD chamber. We tilted the sample by 45 degree, and I will show you the advantages. This is 5-degree tilted, which is almost like flat, and you can see there are lots of defects in the graphene that you develop. But if you have 45-degree tilting, you can see that the surface is almost free of any defect. So that tilting was very helpful. 5-degree tilting, again, we did Raman spectroscopy, and we could show that if you have 5-degree tilted sample, the graphene is not uniform, and you will appreciate it more when I say take you to the 45-degree tilted sample. On the entire surface, graphene coating is uniform, as we could show by Raman spectroscopy. You can see that Raman results are same for all the points, whereas Raman results are not consistent for different points if you have 5-degree tilting. So 45-degree tilted samples gave very good better corrosion resistance, and that was proved by electrochemical testing, as you can see, and also post-corrosion analysis. You can see 45-degree tilted sample didn't have as much damage. It is in much better condition as compared to 5-degree tilted sample, which underwent corrosion attack. We take pride in showing you what I'm showing you now, that for the first time we use scanning photoelectron microscopy. It is nothing but XPS, but instead of getting a simple spectrum for a point, you are doing imaging on the entire surface. And you can see that 5-degree tilted sample had quite a lot of disrupted area which exposed the nickel substrate, and that's why you can get nickel signals on 5-degree tilted sample. Wherever you get nickel signal, carbon is not there because the coating was not good enough, and because nickel was exposed to the sulfuric acid environment, you get sulfur signal as well. As opposed to that, 45-degree tilted sample did not show any nickel at all. There was not much of disruption, as you saw earlier, that there is not much disruption on the surface. And there is beautiful uniform carbon signal across the entire surface, and also there is no sulfur signal, means there was not much attack. I come to the last part of my talk. I hope that I have about 5 minutes. I can finish this interesting part of the story. So how about mild steel? Can we develop coating on mild steel? It is challenging to develop graphene coating by CVD on mild steel, for simple reason. I don't know whether there is any metallurgist in the audience, because at 1000 degrees Celsius, mild steel will have face-centered cubic structure, but at room temperature, it has body-centered cubic structure. That's fine. That's metallurgical fact. But the problem happens because face-centered cubic structure at 1000 degrees Celsius has 100 times greater solubility of carbon compared to body-centered cubic structure at room temperature. So what will happen at 1000 degrees Celsius, steel will be absorbing or will be solubilizing quite a lot of carbon. And when you cool down, it will transform to BCC, and all of a sudden it will reject a lot of carbon because FCC has 100 times greater carbon solubility. That is a challenging situation. If you have uncontrolled release of carbon, uncontrolled diffusion of carbon to the surface, that does not meet the criteria of controlled supply for graphene development. And because of that particular reason, I'm not going through other reasons, it is a non-trivial task. It is almost impossible task to develop graphene on mild steel. But if one could develop graphene on mild steel, we are talking about no use of stainless steel. Graphene coated mild steel will work better in a more durable fashion to give corrosion resistance. You don't have need of maintaining coating because it does not degrade at all. Good news is that we have managed to develop graphene on mild steel, which gave durable corrosion resistance And for that, we had to do some surface modification. This work was published just 6 months ago in this journal. As I said earlier, I don't have time to go through the details. I will go through remaining few slides, and I hope that you will enjoy how people imagine things and it does not work. We undertook obvious measure for surface modification, and that was unsuccessful. Then we undertook what we call innovative approach of surface modification, but it did not work until we optimized the condition, and then it worked. So I showed you earlier that it is easier to develop multi-layer graphene on nickel. So how about just putting a thin layer of nickel on mild steel, and then you develop graphene on nickel. Top surface is nickel. It does not work. So reason is very simple. The carbon that you produced because of splitting of hydrocarbon during CVD, that carbon will not stay in nickel layer. It will continue to diffuse into mild steel. Mild steel also has huge solubility of carbon. So you lose carbon that you require for graphene development. And as a result, no graphene was developed. Raman spectroscopy showed no graphene. Those G or 2D peaks are not there. And there's not much improvement in corrosion resistance, even if you put a nickel layer, because you lost all the carbon that you required for graphene development. So what you do, you want to stop carbon from diffusing. This is the top nickel layer. You don't want carbon to diffuse to mild steel. You remember I said that copper has very poor or very low, insignificant solubility of carbon. Why don't we put a layer of copper in between nickel and mild steel, so that carbon that is solubilizing in the nickel in the early part of CVD will not get to mild steel. It will not leak. It will not leak into mild steel. Copper will stop because copper does not have solubility of carbon. We did that. Just put arbitrarily a layer of copper and a thin layer of nickel and try to develop graphene. It did not work, simply because now copper was diffusing to the nickel surface, and also mild steel was diffusing. Both iron and copper can diffuse through nickel. It was coming to the surface and it was jeopardizing the graphene development. Again, we did not have surface. So what we did, that we took into account the time temperature window, how long it will take for mild steel or copper to diffuse through the nickel layer to come to the surface. And accordingly, we decided the thickness of copper layer and nickel layer. And that was about 10 to 12 micron of copper layer and 10 to 12 micron of nickel layer. And we developed that kind of optimized layer. And then we could develop very good quality graphene. You can see no defects. G peak is taller than 2D peak, is multi-layer graphene, and that gave us very, very good corrosion resistance. As you can see here, that graphene developed on nickel that was plated on copper, and copper was plated on mild steel. So graphene coated mild steel gave very good corrosion resistance. As you can see, again, couple of orders of magnitude superior. Whereas without graphene, we didn't have much improvement. And that is what is shown in the polarization plots or in the EIS plots. And that graphene gave very good corrosion resistance. It is statistically validated data, and there is no reason why this should not last forever. As I said earlier, the graphene will not deteriorate at all, whereas just nickel or copper coated one without graphene did not give as much improvement in corrosion resistance. It was all because of graphene. So what I showed you today is that graphene is a unique material. Having its coating on metallic substrates is innovative or is disruptive, as a matter of fact, because it gives so much corrosion resistance, which will be everlasting. This coating will not deteriorate. And it is innovative because using the metallurgical principles or diffusion principles, we could identify the relative thicknesses of copper and nickel layers. And that was innovative aspect. And we're addressing the problem of corrosion. So I hope that I addressed all the 3 points, that it is innovative approach, It is disruptive approach, and it is addressing the problem of corrosion resistance using the modern material that is graphene. Thank you very much.